So, this video is a companion to a post on my blog, which is called I Am Stephen Ball. The blog is called that. That's the title of the blog. I know. Get over it, okay? And if you don't know any chemistry, this won't make any sense to you. Or if you've maybe read some of the posts on the blog, maybe even a little bit, then it might make sense. I doubt it, because you're pretty stupid, but we're going to try anyway. We're going to try, okay, to explain this concept of tetrahedral stereogenic centers, which I initially attempted to explain using the written word, and that doesn't work very well for this. I tried to use images. I made some images. They look like crap. I hope a video will work better because I get to use models. I'd prefer to use ball and stick models, but I don't have any. So we get this kind of model. I don't know what kind of model to call it. I don't know what to call this, but what this represents is an sp3 hybridized carbon atom in the center. sp3 hybridized carbon atom. That just means, I know, sp3 hybridized carbon atom, what's that? Okay, shut up. Just shut up. This carbon atom is attached to 4 things, okay? That's it, 4 things. In this case, since it's a chiral center, a tetrahedral stereogenic, we'll just call them chiral centers, okay? We're just going to call it a chiral center, because I know you're, yeah, okay. It's a chiral center, and it's attached to 4 different things. So let's add some things so that because it's not attached to 3. I know you're thinking, okay, it's not attached to 3 of one thing and 1 of another. It's not attached to 2 of one thing and 2 of another. It's not attached to 2 of one thing and 1 of another and 1 of a third thing. It's attached to 4 different things. And this one is attached to pink, red, white, and black. What atoms or groups of atoms that represents, I don't care, okay? For this demonstration, for those purposes, it's just pink, red, white, and black. That's what we'll call them. What I also have is the molecule's twin. I know, isn't it precious? I'm holding them both by the pink. They have a red, a white, and a black. They're spinning. And they're twins. Wrong! You're wrong. They're not twins. Okay? They're not. They may look like they're identical. They both have carbon in the middle. Pink, white, red, black. But they're not identical. You doubt me. You doubt me. Observe. Pink on top. Blacks line up. If I can move them in front of the camera. The whites and the reds, they don't match. What's wrong with that? Now, you're probably thinking that you could orient these in space somehow. Maybe be sure that the red lines up, and then be sure that the white also lines up, and if you could just do that, that it will work. That you'll have it lined up. Well, you can get the reds and the whites to be lined up, like this. They're lined up now. But the pinks and the blacks aren't now. No matter how you do this, you can't superimpose them on each other. And that's because they're not the same molecule. They are not identical. What you could do to fix this is break away 2 groups like I just did. Now red and white have been switched. Now they superimpose just fine. Blacks are together, reds are together, whites are together, and finally pinks. Everything's good. But this property called chirality comes in. And because this molecule is chiral, if it were to look in a mirror, and no, it can't actually look in a mirror. Don't think that way. This is just hypothetical. Molecules cannot look at anything. They don't have eyes. But its reflection, it would hypothetically see, if the pink were in the back facing away from the mirror, my hand is about where the mirror is. The black is on the bottom, let's say. So red's facing toward you and white's facing toward me. Well, if the molecules, if we have the same molecule over here, it's not a mirror image. The reds, you have a red and a white facing you now. So what I'm going to do is I'm going to take the one that was in the mirror and now switch it so that now we get a working mirror image. But again, these aren't the same molecules anymore because I made another switch. The pinks are in the back on both, the black's on the bottom, red's facing you, white's facing me. The mirror image works, but superposition, or superimposition rather, they're not superimposable. They're not. It doesn't work. That property is called chirality, and these two molecules are called enantiomers of each other. They are non-superimposable mirror images of each other. That means enantio. That's what enantiomers means. I know it's a big word. Don't get thrown off by it. So this is not the only way to have chirality. Don't think that it is, but you don't want to worry about the other ways to have chirality right now because you're slow and you panic easily, you get confused. Let's just stick with this one for now, okay? We have two molecules that look very close to each other. If we put them across from each other, it's like it's looking in a mirror. But they're not the same. They're not the same. If I make the switch, then they are the same. To reiterate, since you're probably going to get this wrong anyway, but I'm going to try. It only works if all four groups are different. I just removed the pinks. Now, each of these has two blacks, a white and a red. It's very easy now to superimpose them. We have black with black, red with red, and white with white. They all also make nice mirror images of each other. If I turn them the right way, that is. They're mirror images, they're superimposable. They're not chiral. Also, if a molecule has one chiral center, as these all have, one chiral center, the molecule itself is chiral. It's non-superimposable on its mirror image. If it has more than one, the molecule itself might be superimposable on its mirror image. It gets complicated. So keep that in mind. Just because a molecule has a chiral center doesn't mean the molecule has an enantiomer. It might not have any enantiomers because it might be superimposable on itself. It needs to have only one, and not more than one, in order for that to work. And finally, if you are wondering where this comes up, this effect is most famous for appearing in both proteins and in sugars. Bye now.